Hello everyone, today we are going to learn how to develop a simulation of a centrifugal pump. In this case using Ansys Fluent. We are going to have a pump whose impeller will only have 5 at a time, and we can obtain a simulation as shown below. The boundary conditions are that a flow of 86.11 kilograms per second will enter this centrifugal pump, and we are going to consider a pressure that we will see in the simulation constantly. All these files can be downloaded from the video description, both the geometry and the mesh. I am sure that this tutorial will be very helpful. Let's begin. The first thing we are going to do is download the file. I leave you the download link in the video description. Once you download it, unzip it. We are going to open it here to see the content, and in this case we have 4 files. 2 files that are step and IJs belong to what is the geometry of the pump. Both impeller and volute, and the other 2 files MSH and CGNS correspond to what is the mesh. With these files you can modify them if you want to adapt them to your project, and they will also serve as a guide for you to complete this tutorial. I advise you to always work in step format. However, if you want to open it in another program such as Inventor, SolidWorks or another, then use this format. That is compatible with most CAD's programs. Once you download it, in this case I will go to Workbench. Open it. In this case we will open the content to view it. We go here Geometry, here in Geometry. We will open here, right click, Import Geometry. I will look for it. In this case it is on the desktop where I downloaded it. I enter the download folder, and in this case I will choose Ansys Fluent pump.stp. I open it. Now I right click and place here in Edit Geometry in Design Model. We choose Import and then Generate. Ready. With that we have the geometry here. In the worktree you will be able to see that we have 2 solids. One corresponds to the volute and the other corresponds to the impeller. In this case this impeller only has 5 blades. If you want, as I had mentioned, you can modify or scale it as you see fit. Let's close it, and now we're going to go to the mesh. We go here to Mesh, right click, place it in Edit. We're going to open the Ansys smashing program first, and the next thing we're going to do here is import the mesh. How do we import it? Here we go to File, Import, select Mesh. But before that it's also going to be necessary to import the geometry. We're going to import the geometry. In this case, we select here. I'm in the download folder. I select in this case Ansys Fluent pump.stp. The one we opened in Design Modeler. Open it. Let's wait a few seconds for the geometry to load. If a message like this appears, just ignore it. Click Accept here. Here we return the geometry. Perfect, we have it. No, we already have the geometry here, and once the geometry is open, if you want to have a mesh, you can start generating the mesh here. In this case, when you select mesh, everything here appears disabled. Don't worry, all you have to do is close the program, and again you go to mesh. Select it, right click and click on Edit, and once open you select mesh. And now you have the options here to be able to generate your mesh from the geometry. We are going to generate a default mesh here where it says Mechan. We are going to change it for CFD, and we are going to leave it in Fluent for example. We click on Generate and the default mesh is finished. No. Here as you can see everything is seen. There is no problem or error message. Everything is correct here. You can refine the mesh as you consider pertinent. Since we already have a mesh that is in mesh format, we are going to work on it directly there. But in this case we are not going to open Ansys Smashing, but since we already have a mesh ready, we are going to open it directly in Ansys Fluent. If you want to generate your mesh here, the only thing you have to do once you generate it is name the boundary conditions and then select Fluent here. Place it on Mesh, right click, Update, and all the information that is here will go to the Ansys Fluent setup. Here you start the configuration that we're going to do next. That is, the process is exactly the same, except you're working with a mesh that you generated yourself. And that's it. As you can see, it's checked here, which indicates that the geometry is working correctly. Next, we're going to work directly with the mesh we already have from the download we created. You go here to Fluent. I'm going to put it here. All right, we go to Setup, right-click and click on Edit. This window will appear here. You are going to put the processors that you have available on your computer. In this case, I go here to the Task Manager, and in the Task Manager for my computer I deserve this option here, which is called Performance. If you use Windows 10 here, you should see the Performance tab, the Mediones, and in this case here it indicates the number of cores available in your processor. Cores also appear here, which are 16. You have to ignore the logical processors since for CFD we use what are called cores. Then the value that you have here, you are going to put it in this solver processes box. In this case I am going to put 16 here. It is also important to remember that if you are using the academic license you will only have 4 cores. If you are going to work with an academic license you can necessarily only put the value of 4 here, because if you continue with the simulation a license error will appear. If you want more precision so that it considers more decimals active here, double precision, you can leave it like that. If you want here in the dimensions, this simulation will be in 3 dimensions. We click on Start, and with that it will open Ansys Fluent. We will wait for the program to load, and once loaded we have nothing here. We will import the mesh that we have downloaded. We go here to File. Then from File we go here to Import, and we will select Mesh here where it says Mesh. We will go to the folder. In this case you go to the desktop. Here I have the folder. In this case you cannot see anything because the format is by default in MSH H5. You are going to change, and you are going to choose this second option, which is MCH. Selected, and now you can see the mesh selected, and click OK. With that we are going to wait a few seconds for the mesh to load completely. Ready. In this case I already have my geometry here. I have the mesh. By pressing the middle mouse button you can rotate your geometry to be able to see. Here is the input condition. The input condition exit, the condition of contact between the impeller and the volute that is already configured by default in the mesh. If you are going to work with the geometry when generating the mesh in Ansys Matchin, you will necessarily have to place those boundary conditions. You can do a check here, both the mesh and a quality report. In this case there will not be any problem, and if you want to view the mesh you go here to Display. Select Edges. Click on Display here. As you can see the meshing level that we have used for this geometry. Do not deselect edge again. Click on Display, and we have here the original condition. I will click Close, and we will start with the configuration to develop this simulation. Then General, we go here to Models. In this Models section you have all these options. Here you have the option of the turbulence model, which is the main one to appear. In this case we are going to work with K-omega-SST, which is a robust turbulence model for this type of simulations that compete with what are turbines, pumps, or compressors. Let's close. There are no changes other than you're going to do here. In this case we go from Models to Materials. In Materials you double click here. We have in the air fluid part. Obviously the centrifugal pump does not work with air, but in this case it has to be water. You select here at the bottom Create Edit. This window will open. Here we will select our fluid, which in this case would have to be water. If you click here only air appears, so you can see the other materials. You go to this option that says Fluent Database, As all this is in English and in alphabetical order, you go here to the final part where it says water liquid and select it. Once you select it, here in the values of density, specific heat, and other variables corresponding to this material. If you, for example, want to change the density, you can do it, but previously copying this material. So once you select it, you click on Copy. Close it, and here where it says air you are going to choose water in liquid state. Here for example you can change the density and viscosity accordingly. This viscosity that it's here, it corresponds to the dynamic viscosity. Not that it's kilograms per meter per second, but also pascals per second. Then we click on change create and we close it. Ready, very well, it still appears here. Air, in this case I'm not going to work with air, I'm going to work only with water. So I want to delete it, but if you delete it right now, let's see what happens. I'm going to hit air delete, or eliminate. This error message appears. Why? Because even though I have created the material, the air is still configured as the fluid or the material for the volute and the impeller is not. And that's why this message appears here. I'm going to click OK and to correctly configure that. That is, so that only water is passing through the pump. I'm going to go to this option that says Cells on Conditions. Double click here. Let's select the impeller first. Select the impeller. Click Edit here. What you're going to see is that the material with which this geometry is working appears, which in this case says air. Let's change that to water. Ready. Also the impeller, as we can see, is going to be this part of the geometry that is going to be rotating at certain RPMs. So you click here on frame motion, and when you have frame motion activated, new ones appear here below options. You have to choose here, for example, the axis of rotation. If you observe, in this case the rotation axis is going to be on the z-axis. Then z is going in this case from 0 to 1. It is not the rotation axis, and observe that 0 would be here. And 1 would be here, not in the sense of the z vector that appears here. Very well, then it is correct. If your axis of rotation is in n or in x, you would have to change here from 0 to 1 if it were I, here from 0 to 1 if it were in x. In this case we are going to leave it by default. The other thing you have to change is the rotational speed. In this case the rotational speed is in radians per second. However, our impeller is designed to operate at 1600 RPMs. At least this impeller that has 5 at a time, you can do the conversion. But there is an easier way to convert these radians per second to RPMs. We go here to the units part. Select it here. You are going to search for angular velocity. Select it and observe that it is marked by default radians per second. I'm going to select revolutions per minute, and when you select this value the unit will change. You select it, it automatically change. You close it, and now it's the angular velocity. In revolutions per minute here we're going to put the value of 1600. Important. How to know if this value of the angular velocity is positive, negative? Here you have to use the right hand rule. In this case the thumb has to point in the z, and then you have to turn as you learned in the mechanics course, possibly not. Then this would have to turn in this direction to be consistent with the position of the volute, with which it has to be 1600 positive. No, because if I put negative it would turn in the opposite direction, which would not be consistent for the simulation that I'm developing. You hit apply. Correct. Very good. Now we hit enclose and we go to the second solid, the second geometry, which happens to be the volute. We hit edit, and in this case the volute is not going to rotate. It will stay in a single position. The only thing we're going to change is the material here. Instead of air it has to be water. You select it. We're not going to change anything here. You hit apply and then close. Now we have indicated to the program that the fluid that is going to pass through both the impeller and the volute is only water. We return to materials. We double click, and now if you select air here we select it and hit delete, and now it is deleted and no error message appears. That indicates that both the impeller and the volute are being configured for what is water. No, if later we want to analyze the capacity, that can be done. We would also have to place water vapor here as another material. Very well, we have already defined the conditions. Now we go to boundary conditions. In boundary conditions we have to indicate what the inlet and outlet conditions are. We have already named that in the mesh that I will also name Ansys machine. Here we are only going to place the value that corresponds to each boundary condition. We first go to inlet, which is this blue area where the flow. We double-click here, it is configured for velocity. However, in this impeller what we are going to do is place a mass flow. What is the mass flow? Equal to the density times the flow rate. I am going to go here where it says velocity inlet. We are going to select here the option of max flow inlet or mass flow the entrance. You selected there, this window opens here. So what is going to be the mass flow? We are going to consider in this case 86.11. The design of the impeller has been for this mass flow. We are not going to make any more changes here. I click apply and then I click close. I have already configured the flow that is going to enter through this blue area. Now we are going to configure the exit area, which comes to be this one that is in red. We double click and once the window opens, you will have to place the manometric pressure here. No. This option comes to be the manometric pressure. I'm going to leave it at the default value of 0. You can change this later if you want to make or generate some curve for some graph. But in this case we are going to indicate that the value is going to be 0. Not the gauge pressure. We hit apply. We don't make any changes there and then I hit close. Very well. Now I'm going to focus on the impeller to generate the boundary conditions. The impeller obviously has to be moving. However, this simulation is stationary. That is, we are going to create a fictitious movement in order to obtain the convergence quickly. Since if we wanted to do a transient simulation, this would take a lot of time, especially because of the current number that we would have to calculate. So what we are going to do next is define the parts of the impeller that are going to be rotating. For example, one part that is going to be rotating is going to be the blades. You select. With a double click here on the blades part, it says wall movement. It says stationary wall. It is not going to be stationary because we are going to create the movement fictitious of that. You put here moving wall, and when you put moving wall here it says rotational. You activate this option since it will have a rotational turn. The axis will continue to be Z here. It says relative to the adjacent area. Know what this option means? When you put this option, it means that this part that comes to be the blades will rotate according to the 1600 revolutions per minute that you already configured in Celsin. Conditions correct. So here you leave it at 0. Why reason? Because the angular velocity is already configured. In Celsin conditions here it says that it will be relative to that area. That's why you simply leave it there. That means that the blade will be rotating at 1600 revolutions per minute. You apply here, then close. Very well. Now we go to hoop and we also have shot. What are those parts? We go here to display to be able to observe it. We are going to see everything first. We are going to place hoop here. I am only going to select inlet, hoop and shout. Okay. Here you deselect everything with this option. We are going to select hoop and then show. Display. Then this part becomes hoop. We are going to put hoop first. We select this and it becomes the lower part of the impeller. No, this part will also be rotating at 1600 revolutions per minute and would only be adjacent to the Celsin that we already configured. We go here to shoot, which is the upper part of the impeller, correct. The wing, which is also what will be rotating according to the movement of the impeller. Then the axis we go here to display to see. That will also be rotating at 1600 revolutions only. Here we have a fixed zone. What is this fixed zone? I am going to select it. I click on display and it comes to be this area external to the axis. This area external to the axis is separated from the impeller imaginarily in this simulation. So it will not move. It is as if it were a large tube that will simply direct the flow. Another thing that is not going to move is this tip condition. We select it. Display and that tip comes to be a small space that is around the impeller. It comes to be like a space between the impeller and the volute that will also be without movement of the 1600 revolutions per minute. No, and there is nothing else. I will activate everything again to see the complete pump display. Close, with that you can help to place the conditions corresponding to your simulation. Then we go through hoop first, then the lower part. Here you click on edit, and in this moving wall option check here in the rotational part. 01, and it has to be in Z. This is relative the Celsius condition, which was 1600 revolutions per minute. You click on apply. Close, we go to shoot. Here in edit we make the same configuration. Here moving wool relative to being adjacent zone. Such optional from 0 to 1 apply and then close. Then we go to the axis option. When you select axis, by default here in type axis will appear. We have to change. We are going to choose here in this case wall as it was the condition of the others that we already selected. This window opens. You repeat the same process, moving wall relative to adjacent zone. Rotational, and you click on apply. Ready. From there nothing is needed. Only the fixed part that was the one that directed the flow that comes to be fixed here. No. Then fix it is also a wall condition. Wall, you click on edit, we click here on moving wall. But in this case this section of the fixed wall or the fixed pipe that is directing the flow will no longer be relative adjacent. Here we also put rotational to know that it is the axis of rotation, the z-axis. But it will no longer be relative to the adjacent Celsius, which comes to be 1600 revolutions per minute. But we are going to put here the absolute option. What does this mean? When you put absolute, there you have to configure the speed that is here, which is the revolutions per minute. When I put the value of 0 here, it means that the fixed part is not going to move. No. While the first option adapted the speed already configured in Celsius conditions. Absolutely, the speed is going to configure according to the value that appears here, and if I put 0 it simply means it is not going to move. I hit apply and then close. Very well, we are going to do the same for tip. You select it is in wall, in this window moving wall. Again here absolute movement of 0 meters per second. Or 0 revolutions per minute here in rotational from 0 to 1, and you hit apply. With that we already completely configure the impeller part. Now we have to go with the volute part, and for that we select the volute wall here. It is also a wall condition. You click on edit, and in this case when you have the window here the volute will not move, and it is not necessary to configure moving wall because when we configured in Celsius conditions we did not make any configuration regarding the rotation. That is, what is here by default. You simply click on apply and close. No. And now what we would be missing would be the contacts that are defined here by default. When you import mesh to these interface conditions will automatically appear. If you click here on edit, it appears that this is the interface condition that also coincides with wall 19 and wall 18. What are the interface conditions? This that is in yellow. That is, one wall corresponds to the limit of the volute and another wall corresponds to the limit of the impeller that they are in contact, and the software does that automatically. What you do have to name when you make or generate mesh in Ansys. Machine. No, here you have mesh interfaces or mesh interfaces. We are going to open here so that you can visualize it. Here we have the two conditions. Here is the interface created between them. Here you do not have to modify anything, we simply close it, and now we go to the methods condition. We double click here. Yes, we have to make some important configurations. The first thing is that it says here coupled. We are going to change it to simple in order to obtain a rapid convergence. Then where it says second order pressure in this spatial discretization area, we are going to choose Presto. Why Presto? Presto is a type of interpolation scheme widely used for rotating flows, which in this case is that of the pump. That is why we select it. Then to have a rapid convergence, where it says here momentum turbulent kinetic energy, the specific dissipation ratio, All of this we are going to change to first order. Now if you wish after doing this first simulation, you can change it to second order to have greater precision. But in this case my objective is to achieve convergence. Precision issues we can see later in another tutorial. Then we can correct the gradient with this option. We are going to check it. I recommend that you do it too if you are going to follow this tutorial. If you are doing another, I recommend being able to validate it previously. Then we go here to control. Here we are going to make some changes. These are over-relaxation factors. These over-relaxation factors allow me to find convergence faster. Many times if we leave these default values, it is possible that convergence is not reached. In order to find convergence quickly, despite the fact that we have already configured the scheme in first order, it will be necessary to make some nuances here. And obviously when the results are obtained they have to be validated with an experiment to see if the results obtained by the pump coincide with the values that we have obtained in the experimentation. We're going to change momentum to 0.5 here, turbulent kinetic energy to 0.4. The specific dissipation ratio to 0.3, and we're going to leave turbulent viscosity at 1. That is, we're changing these three factors that are mainly related to the turbulence model, which is one of the key factors that often prevent rapid convergence. Okay, ready, we have that. Now we go to initialization. For initialization we have two options. We are going to activate the hybrid option. Initialize, and in this case it is counting up to 10 to start faster with the values that we have imposed for the boundary conditions. Now we go to room calculation. We double click here, and in this case we are going to choose a fairly high number of iterations. I am going to put the value of 4800 here. If it does not reach convergence but I see that it is falling, then I can increase this value a little more, and if not it will automatically stop before reaching this iteration. We do the calculation and we just have to wait. Then here we can see that it is descending. We will wait to see how long it will take to obtain the results. After a few minutes the simulation has concluded. A message will appear like this: calculation completed. We click OK up here. Visualize in which iteration it reached convergence. In this case it was in 998. Very good. We can visualize the results here. Let's see, wait a moment here, scale of residues in. You can see that the convergence has been continuous, constant, and largely by mesh. Also the configurations that we have developed. Let's close Ansys Fluent. Here we have forgotten something very important, which is to always save our file. We will do it now. Otherwise this simulation will be in the temporary files. We go here, File, Save As. I will save it in this case also on the desktop, and I will put here Ansys Fluent Pump. Ready. So this is the file with which I am working. To be able to visualize the results I will go here to Results. There it is, option here, and I will place it on Solution. Ready. You can also visualize the results directly in Ansys F. However, working on them in Post-FD is much simpler. Very well, here we have it. Now let's activate the options. I go to this option here, Contour. I click on Open here in Contour where it says Locations. We are going to select everything, both volute and impeller, all the faces. We click OK. Here I am going to change pressure from global to local, and I click on Apply. Here we can observe the pressures that in this case the simulation presents. As we only have 11 contour levels, in order to have a smoother visualization, we will change this to 120. I hit Apply, and now I can observe in greater detail the pressure around the centrifugal pump. We can also make a cut in the middle without creating a plane here. For example, we create a plane. In this case the plane would be in XY. Here it is. I'm going to deactivate this contour. Here the volute appears. We are not going to move this plane here on the Z-axis. We are going to go back a little. It would be 0.05. For example, I hit OK. I went a little bit too far. So it would be around 0.3. There it is better. Very well. Once I create that plane, I go here to constant colors by variable, and where it says pressure I am going to activate speed. But in this case the speed has to be this option. Why reason? Because in this case the flow is rotary. You select it, put it here in local and hit apply. No, this corresponds to the impeller. Yes, you want to visualize the topic of the volute selection. In velocity here we would be mainly starting the volute no. All this here you know that you always have to validate or calculate with some type of equation that involves the velocity triangle or design calculation for pumps no. Also what we can see here are the velocity vectors. I am going to deactivate in this case plane 1. I go here to the vector area. I put here vector. Location, we are going to choose that plane 1 that we have previously created. Here where it says color we are going to change by variable and you are going to choose. In this case, this option here glow bar by local we click. On apply here we have the velocity vectors for our pump. Well friends, I hope this video has been helpful to you. You know that you can download the material from the link that I leave in the description of the video. I am sure that it will be very helpful for any other pump or turbomachine project that you want to simulate. Without further ado, we see each other, and any type of doubt or query you can do it in the comments. Greetings all.